Alright, so this video is a tutorial of how to use the Black Scholes option pricing model. The model we're going to look at does not include dividends, so we're assuming that the stock we're looking at does not pay dividends. We would add the dividend yield in here if it did. The Black Scholes option pricing model was developed by Black and Scholes in 1973. Soon after that, the Chicago Board Option Exchange came into existence, and so it was used as a tool to be able to determine the value of an option. We're going to look at call options and pricing call options using this model today. The Black Scholes option pricing model actually has three different equations in there. There's the value equation where V is equal to the value of the call option, and then that's equal to the current price of the underlying stock multiplied by a probability that a deviation of less than D1, which we'll calculate here as D1, will occur in a standard normal distribution. Apologize for the spacing here. As a result, in D1 and in D2, so that we see in this equation, represent areas under a standard normal distribution function. And that's important to know because later on we're going to use Z distribution results to determine the value of the option. X is the exercise or strike price of the option, which we'll use in the D1 calculation. RF is the risk-free rate. T is the time until the option expires, and this is usually in years. So for 1 year, T would be equal to 1. For 6 months, T would be equal to 0.5. And then sigma squared is the variance of the rate of return of the stock, or the standard deviation here if it's not squared. That's often calculated as the standard deviation, the annualized standard deviation over the past 90 days for the stock. So what I'm going to do today is go through two problems using the Black Scholes option pricing model, and then talking a little bit about how changes in each of our inputs, the price, the exercise price, the risk-free rate, the standard deviation, and time, affect the value of the option. Okay. So the first example we're going to look at we're going to say the price of a stock So the current price of the stock today is equal to $50. The exercise price of the option is $55. The standard deviation, or the sigma, as we'll refer to it, is equal to 25%, or 0.25. And the risk-free rate is equal to 5%. Typically for problems like this, you want to match up the risk-free rate with the maturity of the option. So if we're looking at a 1 year to the option maturity, we'd want to find the risk-free rate on a 1 year T-bill, or the rate of return on a 1 year T-bill. So putting these into our D1 calculation, because that's what we have to start with. So we're going to take the natural log of $50 divided by $55 plus the risk-free rate of 5%. Our sigma is 0.25, so sigma squared is 0.25 squared. And time, don't have it up here, we're going to say that this option has an exercise date 1 year from now. So if I calculate this, I'm going to start off with the first argument, 50 divided by 55. And then we're going to take the natural log of that. Whenever the stock price is less than the exercise price, as it is in this case, the natural log of the stock price divided by the exercise price will be negative. So you should expect to see a negative number here. So this is negative 0.0953. The risk-free rate is 5% plus the 0.25 squared divided by 2. So I'm going to start with the second argument there. I'm going to take 0.25 x squared divided by 2, which is 0.0313 plus the risk-free rate of 0.05. And we'd multiply that by 1, which doesn't have any effect. So we get 0.0813. And then the denominator is sigma, or the volatility, multiplied by the square root of time. The square root of 1 is 1, so we don't need to do anything there. That's 0.25. And so our D1 is going to be equal to 0.0953 negative plus 0.0813 divided by 0.25, or negative 0.056. D2 then, if we go back up here, to find D2 we take D1 and subtract out sigma times the square root of time. Grab that and pull it over here. So D2 is equal to D1. D1 was negative 0.056, and the sigma times the square root of time, we calculated that just a minute ago, is equal to 0.25. So this is negative 0.056 minus 0.25, which gives us a D2 value of negative 0.3060. So that's the first two equations. The last equation then is first we have to determine the probabilities associated with the D1 and D2 values, and then we can fill in our value equation. To find the values for D1 and D2, we're going to look these up on a z-distribution table. If you're using a computer and you have Excel, you can actually use Excel to find these, but for our purposes in class, we're going to use a z-distribution table. I handed this out in one of the sections of the class today, but not the other. It is out online on D2L. So my first value was D1, it's negative 0.056. So on the z-distribution table, it only goes out to the hundredths value, so this is going to be an estimated value. So we'll go down to negative 0.0, and the number was negative 0.056. So we want to go over and round this. We're going to round it to negative 0.06, so we're looking in this column. and we'll go to negative 0 and go over. This is for 0, 1, 2, 3, 4, 5, 6. I need to move that a little bit. Okay. And so we get a value of 0.4761. And then ND2 was negative 0.3060, so we would round this to negative 0.31. So on the Z distribution table, I'm going to go to negative 0.3. So here's negative 0.3, and this would be negative 0.30, and then negative 0.31 would be 0.3783. And then I'll fill in the rest of my numbers here. P, in this case, is equal to 50. X is 55. To find the exponent raised to the negative risk-free rate times time, I'm going to put in 0.05. And then you'd multiply that by time. In this case, it's just 1, so you get 0.05. Then make that negative, and then press second. In the natural log button, you see the exponent function above that, so I press second to get that exponential function, and it gives me a value of 0.9512. And what you're doing in this case is actually discounting that $55 back to today to get a value there. Okay. So after I do all that, I can determine the value of the option, which would be $50 multiplied by a probability 0.4761. Let's store that. Then I'm going to calculate the second argument, 55, multiplied by 0.9512, multiplied by 0.3783. That gives me a value of 1979. Store that. So our value would be 2381 minus 1779 or 1979, which gives me a value of $4.01. So if our inputs are accurate, if it's 1 year to the exercise date, 0.05 is the risk-free rate, the sigma is 0.25, or the volatility of the stock prices is 0.25, then we would get a value, we would be able to sell that on the market today for $4. Okay. So that's our first example. For the second example, we're going to value an in-the-money option, which means that the exercise price is greater than the stock price, or excuse me, the exercise price is less than the stock price, and we're going to also choose a time that's less than 1 year. So for our second example, we'll choose a price of $80, an exercise price of $70, a sigma of 0.20, a time of 6 months, and a risk-free rate of 4%. So again, starting with the first equation, the D1 equation, we'd calculate the natural log of 80 divided by 70, a risk-free rate again of 4%, sigma would be 0.2, and time is going to be 0.5. In the denominator, we're going to change that to 0.2, and again time is 0.5. So I'll calculate the first argument, 80 divided by 70. And because the stock price is greater than the strike price in this case, our answer should be greater than 0. So it'll be a positive answer here. So we get 0.1335. For the second argument, I'll start in the top portion. I'll start with 0.2 squared divided by 2 plus the risk-free rate of 0.04 multiplied by 0.5, which gives us an answer of 0.03. And then on the bottom we'll take 0.5 squared, or excuse me, the square root of 0.5 multiplied by 0.2, which gives us an answer of 0.1414. Okay. So this is what you should have after doing those calculations, 0.1335 plus 0.03 divided by 0.1414, which gives you an answer of 1.1563. Alright, so since we have D1, now we'll calculate D2. So D2 is equal to D1, 1.1563, minus 0.2 multiplied by the square root of 0.5. So we have 1.1563. I'm going to store that. 0.5 square root, so I'm calculating this, multiplied by 0.2 equals 0.1414. So I'm going to take the 1.1563, subtract out the 0.1414 to get 1.0149. And now we need to fill in those, determine what ND1 and ND2 are. So ND1, we're going to look up 1.16 because we'll round it to the hundredths. So I'm looking for 1.16, so I'm going to go down to where it says 1, 1.1, and then I'm going to, so this go over to the sixth place. So this is going to be 1.10, this is 1.1, oops. Here we go, 1.10, 1.11, 1.12, 1.13, 1.14, 1.15, and 1.16 would be right here at 0.8770. Then ND2, for that we're going to look up 1.01. So I'll start at 1, go, this is 1.00 and this is 1.01, 0.8438. And now I can fill in my numbers to the value equation. So my price is $80. So the price is $80. The normal distribution of D1 is 0.8770. The exercise price is $70. The risk-free rate is 4%. Time is 0.5. And then the normal distribution of D2 is 1.0149. Oh, excuse me, 0.8438. Right. And so calculating that gives me the first argument is 0.8 multiplied by 0.8770. So it's going to be, oh, sorry, that's not right. It'd be 80, not 0.8. 80 multiplied by 0.8770. So I get $70.16. And the second argument, I'm going to start here. I'm going to take negative 0.045. Excuse me, negative 0.04 multiplied by 0.5 to get negative 0.02, then press second, the natural log button to get that exponential function. So 0.9802 multiplied by 70 to get 686139. And then I'm going to multiply this by the probability of 0.8438. So I get 5789. I'm going to store that. It's the second number. Recall my first number minus recall of the second number to get $12.26. Now, one thing I want to point out to you here is the amount of the option is $12.26. If we look back at the relationship between the stock price and the exercise price, we know for this call option that the value of the option has to be more than $10. And the reason why it has to be more than $10 is that if it, let's say the value today were $9, or yeah, $9, I could go out and I could buy this call option today for $9. And then if it's an American option, I could exercise it immediately and make $1. Okay, so I pay $9 for my option, and then I'd look at the person that I just bought the option for from, who has to now sell me the stock at $70 and exercise the option. So I would have paid $9 and then received an extra $1 just by exercising the option, which wouldn't make any sense. It would be an arbitrage opportunity, and so it really can't exist in a market. So as a result, we know that this number, even if we don't know the answer, we know that the number has to be more than $10. The last thing I want to talk about in this this video is the relationship between the value of the option and the different inputs. So how does a change in input value affect the value of the stock option? So the first input we'll talk about is the standard deviation, or the sigma of the stock. So sigma, higher volatility pushes up the value of a call option because it increases the likelihood that the stock price is going to be higher, or to hit a higher level than it would be if the stock, the underlying stock and the value of the stock were relatively stable. So as a result, as volatility sigma increases, the value of the call option increases. And this is holding everything else equal, so we're not assuming that the stock price goes down and then with the volatility. If the stock price stays the same but the volatility increases, then we would say the option increases, or the value of the option increases. With time, because a longer period of time gives us an opportunity for the stock price to hit higher levels. As a result, we say that with an increase in time, the value of the option increases. So as the time to the exercise date increases, the value of the call option increases. And this actually causes a problem with valuing executive stock options. Executive stock options often have a time to the exercise date of 10 years, which is much longer than a standard option, and also is longer than an executive usually holds a stock option. 60% of stock options held by CEOs are exercised when they're vested. So as soon as the CEO can sell the stock or exercise the option, they go ahead and do that. So they're not holding them for 10 years. So in many cases, if we're using the Black Scholes model to value an executive stock option or an employee stock option, the value is overstated because we know that the executive or the employee won't wait until the last date, to the exercise date, to actually exercise the stock, because it's part of their compensation, it's part of their pay. They may want that pay for something else. So that's a problem we run into with this, and we have to make accommodations for that when calculating executive stock options. The last variable is the risk-free rate. With a risk-free rate, this is a little bit more difficult to figure out if you're looking at the equation. The math is a little more difficult in finding this, but what we find is that as the risk-free rate increases, the value of the option increases, or the value of the call option increases. So this is what I want you to know from this video. 1, how to value a call option by using the Black Scholes model, and hopefully you are able to do that from the examples that I've provided for you. And then also know how changes in these three inputs, volatility or sigma, that's the variation in the stock price or the stock returns, time, and the risk-free rate affect the value of a call option.